would like to focus on a practical example for research in advanced wireless. Cellular telecommunications have far outpaced other traditional connectivity mediums, with about 70% of the global population today leveraging untethered connectivity. Operator and enterprise 5G deployments are in full swing as innovators and researchers start shaping the next chapter, 6G. There is absolutely a shift towards use of high performance compute as well as AI and ML to start innovation required to meet 6G requirements. So, based on several discussions with leading researchers globally in advanced wireless systems, the following have emerged as table stakes for any next generation platform: ability to access off the shelf accelerated compute easily, readily, instead of custom single purpose black box solutions today; access to cellular over the air network datasets, which is a prerequisite to onboarding machine learning and artificial intelligence algorithms; tool chains that are built for artificial intelligence, both offline and online training, as well as distributed and federated learning; standards compliant, real time, closed loop network as a service to be able to bring the focus to advanced research; ease and programmability of the complete network to be able to define the transformations that are necessary to enable use cases of the future. Use cases like hologram displays that require 1 terabits per second of peak throughput, or Mac schedulers that can support billions of devices. As you look at the research landscape, some of the key challenges today that need to be overcome to address these NG needs include: today, there is slow prototyping with hardware description languages, MATLAB, or simulation frameworks, which take months to prototype. There are numerous custom black boxes that are integrated towards being able to benchmark an algorithm or one specific experiment. There is a lack of scalable, flexible, and standards compliant open platform, which is also equipped with machine learning toolchains. While some configuration can be tweaked through configuration changes, it is difficult to change, extend, or program an operational network in real time. While in the previous slide, we looked at some of the problems that researchers are experiencing with ORAN, Open RAN, and the 3GPP standards as well, wireless networks themselves are becoming open, flexible, and virtualized. New use cases in advanced wireless require a more flexible and cost-effective network architecture. One of the key ingredients to achieve this is virtualization, use of general purpose compute and network hardware, as well as network functions that are implemented in software. Further, we need open interfaces between these virtualized network functions that allow the capability to mix and match software from multiple vendors. In this specific block diagram, you see a simplified version of a 5G deployment based on 3GPP and ORAN specifications. You see we distinguish between the core network, which handles mostly the control plane functions of the network, and it is comprised of At least the access and mobility management function, the AMF, the session management function, the SMF, and a user plane function, UPF. For sure, more sophisticated deployments will have additional network functions. On the radio access network, we have the Open RAN centralized unit, an OCU, and an Open RAN distributed unit, ODU, which can be deployed as a separate virtual network function or in a monolithic mode. The OCU can be further split in a control plane unit and a user plane unit, which allows for more flexible service deployments. In order to implement more sophisticated use cases like network slicing, traffic steering, quality of service optimization, and many more use cases, the ORAN architecture also includes a radio intelligent controller, RIC, which uses the E2 interface to be able to communicate with different elements of the RAN and allows to run XApps or applications that are able to dynamically change network behavior in real time. 5G deployments need radio units, ORAN radio units, which are connected to the ODU over the front haul network, for example, in an ORAN 7.2 split. So, can you build such an open and virtualized private 5G network yourselves? So, as I shared earlier, what I wanted to do in this webinar is use a practical example based on the product that we've developed at NVIDIA, which is an ORAN aligned 7.2 split architecture to be able to showcase how programmability, virtualization, intelligence, cloud native principles can all come together in a full stack. Meet Aerial RAN Collab, an over the air research sandbox to help usher innovations in advanced wireless with machine learning and a programmable 5G full stack. We leverage GPU high performance compute, Kubernetes cloud native stack for a 3GPP compliant and conformant private 5G network that is an ORAN 7.2 blueprint with COTS hardware and C programmable software components from NVIDIA and Open Air Alliance. There's key value pillars that I would like to highlight in this slide. First being access to source code end to end, ability to modify, change network behavior from the layer 1 to the core node. One of the key network elements, the base station, is hosted on a GPU high performance compute, which also means that you have access to machine learning tool chains and libraries, as well as use of a multi-instance GPU architecture to split the GPU to be able to use for other AI workloads of interest. ORAN, Open RAN specifications are used to offer intelligent, virtualized, and fully interoperable open network elements with the GPU as the co-host. Layer 1 or the physical layer of the network is inline accelerated based on Open RAN, ORAN, DSA principles, domain specific architecture principles. We have qualified such a BOM as part of our product development and qualification cycle. We can take a look at an example of an Open RAN solution. In this particular example, this is just a reference. In this example, to set up a research network, we have used two off-the-shelf servers. Again, in this particular example, the servers are from Gigabyte. One server with an Ampere class GPU and a NIC, a Mellanox ConnectX-6 DX NIC, acts as the base station, as the G node B. The second server acts to provide the core node network element functions, the 5G core. You will also need to set up a front haul network with a front haul switch. Again, in this particular example configuration, we are using a Dell front haul switch. For the Grandmaster, or the PTP, for the precision timing synchronization, we are leveraging a Viavi Qualsar Grandmaster. We are also leveraging, for the ORU, a 44R Foxconn ORU. For the UEs, user equipment, we've tested and qualified several such user UEs, more specifically standard and easily available iPhone 14, a Samsung S3, or a Quectel dongle. So this was a particular slide that I wanted to highlight as an example of being able to pull together off-the-shelf compute, software-defined frameworks, and being able to set up and stage an operational lab network for research and innovation purposes using Open RAN principles. This particular demo is available in the ORAN virtual exhibition. The next slide talks about the ability to mix and match software components in addition to the hardware COTS capabilities. Now, if you look at it from a full stack perspective, the physical layer, or the Hi-Fi in an ORAN 7.2 split, resides on an NVIDIA Ampere class GPU. It is integrated with the OpenAir interface stack, in addition to several other L2 plus vendors. But since I'm using research as one of the focus areas here, I'm highlighting OpenAir interface as a software stack that has been integrated with the L1 over an SCF, small cell forum, FAPI, standards defined interface. So the physical layer functions leverage NVIDIA's Aerial SDK to provide an inline accelerated physical layer. The Open Air interface, layer 2 and above, provides the medium access control, or the MAC, and the radio link control over the 5G FAPI interface specified by the small cell forum. On the southbound side, the NVIDIA Layer 1 interfaces and communicates directly to the ORU. In this case, again, to double click and highlight the Open RAN value chain, we have a COTS vendor, Foxconn, that we are leveraging for the ORU interop in this example. The inline GPU acceleration of the entire layer 1 allows for a scalable solution for the base station for the G node B, extending to multiple cells that can be deployed along with other flexible and advanced deployment topologies. In this particular example, or in this particular reference, we have combined the CU and DU to a monolithic G node B. This is deployed in Docker containers, or it can be deployed via Kubernetes services to highlight the cloud native architecture and cloud native services. A quick summary from the last few slides. It's just an on-prem deployment topology view as a reference example to being able to set up an over-the-air operational network with a mix and match of COTS hardware solutions from different vendors and open interfaces and specifications from ORAN. So really the ability, and this is a summary slide that I wanted to highlight, some of the key elements that really drive the Open RAN value chain. Absolutely the ability from a research perspective to develop rapid prototyping techniques, the ability to test and validate and benchmark your solutions in a multi-vendor COTS environment, a private 5G environment. There is no fixed function hardware in an Open RAN solution. You're able to build software-defined, cloud-native, and virtualized services. And lastly, as you look at the future, intelligent and adaptable cognizant networks will require open networks that are programmable to reduce risk as well as to ensure the focus is on innovation in next generation networks. So there is a clip that I would like to play. This is from the ORAN NGRG co-chair, Ravi Sinha. It's a short clip, but it tries to summarize uh, Open RAN next generation initiatives. And so let's just go ahead and play the clip from him. This was something that he and I had put together towards a conference that we just had at NVIDIA.
Today's subject is programmable 5G and 6G networks. By me, by the way, as Anupa introduced me, I'm the one of the chairmen of 6G kind of initiative from ORAN Alliance called NGRG. And definitely a small intro for who we are. So ORAN Alliance, as we all know, that it is one of the largest SDO in terms of solutioning for Open RAN concepts. So generally Open RAN has got the 4 pillars, like just to be open in terms of interface, in terms of solutions and everything, being intelligent, just to have a RIC framework, being virtualized, where like we are promoting our clouds, and of course interoperability, which is the most important in our NGRG introduction. So NGRG is a task force basically to facilitate our ORAN based 6G research. We are a research group, and on the right hand side you can see total kind of 4 operators, 4 vendors including NVIDIA, and of course 3 different representations from academia, 1 from America, 1 from Europe, and 1 from Asia, and 1 cloud vendor, which is Microsoft. So these are our board members, of course, including Gio. And our roadmap is very important. Like our roadmap up to 2030, IMT 2030, we have split into 3 parts. 2022 to 2025, where our major focus is mainly about kind of giving the organization a shape, and then coming up with multiple research reports and white papers, and of course including like our use cases, architecture, and all. 2025, 2027, of course, will be the time where we'll have more collaborations with the SDOs. I think our feeds going to the work groups and functional groups and industry workshop. Workshop is our major focus. At present, 5 of the workshops we have successfully we have organized, and this is one of the hot events for ORAN activities. And at present, 5 of the research reports we have already published under ORAN umbrella. And the 2027-2030 is the alignment with the major 6G research SDOs and like spec SDOs, including 3GPP, IEEE, NSF, TIFG, and many more over there. So major emphasis to the NGRG is the use case architecture, AI/ML, security, research platforms, and sustainability. When we talk about the transition of true cognitive networks, I will go from 5G to 6G, where you can see that like with 5G, we had a fair kind of decoupling of hardware to software, a kind of introduction of centralized cloud and to some extent some distributed cloud as well. SA and NSA kind of core framework, which is also giving it a partial capability to have SBA, service-based architecture. And of course, like our major kind of work on XOL is the part of it, and the RIC framework as a part of it, where RFs and XF is the major area of applications and data monetization. But when we go from there to 6G, as we can see that like native kind of artificial intelligence, native cloud, native security, these are some of the baselines. And of course, like our core needs to be service-based architecture. But so quickly have a kind of next generation overview, as you can see from bottom to top, our infrastructure as a service, platform as a service, and security and post-quantum encryptions. These are the part where AI is fully infused. And on the top of it, on a common infra, on the top of it, you can see a software-driven RAN, transport, and of course, the core will be the major drivers. And just like green to red is all showing that the RAN has come a long way. And of course, transport and core is also kind of in progression. And we are hopeful that the different open sources will bring value to the transport and core as well. So this is a kind of a flavor which is kind of finally managed by the end-to-end SMO. And this whole section is cognitive networks or limitless connectivity. But on the top of it, which is very important, is your service-based architecture and services coming from the automation going all up to the metaverse and Industry 4.0 and all. But I think the major disruption will be that like the services and infrastructure, both of them are being coordinated and SLA'd overall. But the data, what we produce over here, and more than like 20, 30, 40% of it, if we monetize, definitely federated artificial intelligence fabric going the top is very important. And of course, a portal through which we can open up the data for our industrial, our corporate, and government consumption. And if you have any questions, you're free to go.
Networks in the future, they are open networks, they have open interfaces, they're virtualized, there is COTS components. So you really have a multi-vendor landscape, the ability to integrate, interop with multiple vendor solutions. And networks of the future are definitely going to be intelligent networks.